Okay, so welcome to this course on random matrices. I will continue with the proof that we started last time. So before we continue, let me just recall what's going on. What are we trying to do? So we are proving this proposition 20, which is the main result of this subsection. We called it the weak local law. So it states that this error parameter, lambda, so which is if you want, the L infinity norm of these matrices in terms of the matrix entries. So we are controlling the green function Gij in terms of the identity times M. And we want to prove that this thing is small, and we are trying to prove that it is small on this entire domain S, which was this rectangle in the upper half plane. And we do it by using this bootstrapping technique, or multiscale induction. And it proceeds as follows. So let me recall the setup. So we take points in the complex plane. So we pick some value E somewhere on the real axis, which is fixed. And then we start at the point Z0, which is imaginary part 1. And then we go down in tiny steps, in steps of size n to the minus 3. Here we are, n to the minus 3. All the way until we reach the scale n to the minus 1 plus tau. So that's our goal. And so we try to do this by induction, and it works more precisely as follows. So let me define this delta k, which is the error parameter I'm aiming for at scale k. And I define these two events. So this is a probabilistic bootstrapping argument. So it's formulated in terms of these events. So the first event controls theta, and the second event controls lambda. If you recall, theta was the difference between the Stieltjes transforms, and lambda was this quantity that controls the green function. And now precisely what I have to put here is something that you really only see once you start doing the proof. It turns out it works nicely with these choices. And so we have to do an induction, so we have to make sure the initial step holds. And this we did last time. This follows from, this was this lemma that we proved last time, which was for the initial step. So that was, I think, lemma 25. So this is lemma 25. That shows that when eta is 1, then both of these events hold with very high probability. Okay, so this can be formulated by saying that you can take their intersection, and this holds with very high probability, so the complement has this probability. I do the whole estimate for a given epsilon, which in the end will be taken to be arbitrarily small, and a d that I can take arbitrarily large. So that was the starting point of the induction, and we saw we had this sketch. I will not repeat that, but there is this bootstrapping argument. There's a sudden behavior, a change in the behavior of the argument that happens at this k. So we have to consider two cases separately, whether k is larger than capital K or less than or equal to capital K. So let me first. Let me consider the case when little k is strictly less than k, capital K. So then we have to, so what was the idea, if you recall? The idea was to use this bootstrapping philosophy. So you start with a weak hypothesis, and at a given zk, you use the techniques that we've developed to obtain a stronger bound on lambda. And then you move to the next zk by using the Lipschitz continuity of all parameters involved. So let me start by this observation. So this lambda is n squared Lipschitz, simply because it's a Stieltjes transform of a probability measure. So as long as eta is greater than or equal to 1 over n, this is why it's not a Stieltjes transform, it's the difference between Stieltjes transforms. So this follows immediately from its definition on S. So Well, maybe I will come to the, let's see, I want to formulate it like this. Yes, I want to formulate it like this. So on the event, so I will make the assumption that I work on the event omega k minus 1 and psi k minus 1. And I want to show that on the intersection of these two events, the event omega k and psi k hold with very high probability. So on this event, I know that phi, if you recall my function phi, let me review also my function phi. So phi was the indicator function that lambda is less than or equal to n to the minus, I think it was tau over 10. The exponent doesn't really matter, it just has to be sufficiently small. Maybe if some of you recall it, otherwise I can check what my phi was. Let's see. Yes, tau over 10. Okay, so there's some juggling with exponents, which you can. It's easier for you to do in your head than me explaining them to you. If we are on this event psi k minus 1, so in other words, we're on this event at psi k minus 1, you apply the Lipschitz continuity, and you know that when you go from k minus 1 to k, this guy will change by at most 1 over n, right? Because it's n squared Lipschitz, this is an n squared Lipschitz function, you make steps of size n to the minus 3. So this changes by at most 1 over n. The same thing here. And you can put all of these errors, now you want to get this inequality for zk, and then you get an extra error term which is of order 1 over n. And these two things together are going to be smaller than n to the minus tau over 10. That's just because this quantity is much smaller than n to the minus tau over 10. That's by construction. If you recall eta is always, a bit too many things, but eta is always less than minus 1 plus tau. Okay, so that's so this delta k is always going to be greater than or equal to, is always going to be less than or equal to n to the minus tau over 2. And therefore, since I have a minus tau over 10 here, I have enough room. And the following holds. So this is a deterministic statement. Okay. So if I am at this point here, on this event, on this point here, this is my zk, let's say, and this is zk minus 1 zk. On this event associated with zk minus 1, I know deterministically that this is true by Lipschitz continuity. Okay, so now we use lemma 23, which were these estimates on our various quantities y and lambda star and so on. And there were two possible assumptions in lemma 23. One was that eta was bigger than or equal to 1, and the other one was that phi is equal to 1. So let's use now this assumption. We obtain, so it had a phi times something, but I will replace the phi with the indicator function of psi k minus 1, which I can do because on this event psi k minus 1, phi is equal to 1. And then I have yi of k of zk plus I want lambda star and this is bounded by delta k. And if you recall, in fact, in this lemma on the right-hand side, I had this thing that I called psi theta, but I will just estimate the psi theta by this delta k simply by observing that the imaginary part of m plus phi times theta is bounded by is of order 1. Okay, so we had a lemma describing the elementary properties of M, and we saw that this thing is bounded, and this is also bounded on the event phi is equal to 1, simply again because M is bounded. Okay. And now let us exploit this by plugging it into, I think it was called lemma 21. Trying to get my numbers right. Yes, so we had a lemma 21 that gives the self-consistent equation. So if you recall, lemma 21 was the equation for let me just recall what lemma 21 says. I think it's maybe helpful to recall. Lemma 21 says, so by lemma 21, we have, so 1 over GII so this was this yi which we've estimated, so now we know the yi is small. And now let me average over I. So this let me multiply. So I get G times GII. If I multiply by GII on both sides, plus Z times GII plus 1 is equal to YI GII. I can average. I average over I. If I average over I here, I get little g, so I get g squared. G squared plus z times g plus 1 is equal to 1 over n sum over I yi GII. Okay. Now, if I'm working on the event, now I can multiply. So on this thing here, this is equal to delta k, as we just saw. Phi is equal to, on the event phi is equal to 1, this thing is of order delta k. And then I will use this stability result for the roots of the quadratic equation. So if you recall, we had a lemma which I think was called lemma 24, which told you now precisely if you have, now G is a solution of this quadratic equation. The right-hand side is small with high probability, very high probability, and therefore we will find that G has to be close to either M or M tilde, where M and M tilde were the solutions of this quadratic equation, where the right-hand side is equal to 0. So let me summarize that. So using lemma 24. So I want to get statements with very high probability, so I have to unpack the definition of this thing. I will put an n to the epsilon in here. And this lemma says that, so I'm working on this event, as I was here. I'm always working on this event. So if I'm on this event, then the probability that the following event is wrong. So the claim is that this holds. So if you recall, lemma 24 says that if this right-hand side is bounded by n to the epsilon times delta k, then this thing holds. And since we know that this is true with very high probability on this event, we find that the complementary probability has to be small. Okay. Is this okay, everybody? All right. So let me give this guy a name. So this holds. This is an equation sharp that we will use in a minute. So we have established that if I make the induction hypothesis, I know that G is going to be close to one of these two solutions of the quadratic equation. Now I have to make sure that it's close to the right hand, the right one. So how do I make sure that I am close to M and not to M tilde? I use now the bootstrapping assumption. Up to here I only use the bootstrapping assumption psi k minus 1. Now I will use the bootstrapping assumption theta k minus 1. Theta k minus 1 tells me that at the step k minus 1 I was close to the good one, right? And again, by Lipschitz continuity, I will deduce that if at the previous step I was close to the good one, then here I know that I'm close to this one or that one, but because I was close to the good one in the previous one, I have to be close to the good one here as well. We had a diagram last time that kind of explained this philosophy graphically. Now let's try to see how to do that precisely. So by Lipschitz continuity, on omega k minus 1. So omega k minus 1, I recall, controls the error in theta. In other words, this one, G minus M. So omega k minus 1 says that this quantity, G of zk minus 1 minus M of zk minus 1, is bounded by something small. Now I transport this to the next step by Lipschitz continuity. The error I incur is something of order n to the minus 1, which I will absorb into the right-hand side. Simply by including a factor 2 in that estimate. So if you go back to the definition of omega k, you have exactly the same error bound. Here I just add a factor 2, and all I have to make sure is that this guy here, without the factor 2, is much bigger than 1 over n. And that's true. This is an elementary fact about just my definitions of delta k and so on. So if I add another one of these guys, this will account for the error that I made in the Lipschitz argument. Okay, so now we have to make sure that, so I know two things. I know this, and I know that. And if I can establish that this bound is smaller than the separation between M and M tilde, I will know that, in fact, I have to be close to that guy and not that guy. So it might look naive. So what are we in the end trying to do? We're just trying to get rid of this factor 2. Right? What I'm aiming at is to prove this bound without the factor 2. So you could say a factor 2 is not dangerous because, I mean, this is all tiny whether I have a factor 2 or not. is not a problem. But remember, we have to do this induction step in order n to the 3 times. And if you accumulate at each step a 2, in the end you will get a 2 to the n to the 3, which is a disaster. So we have to make sure that this innocent looking factor 2 is in fact not there. So we have to use this estimate, which does not have the factor 2, and combine with this one to get rid of it. And we do that as follows. So by lemma 24. So if you recall, I know that these two guys, so the two solutions of the unperturbed quadratic equation, they are of the order kappa plus eta k. And this, I want to make sure that this thing is much bigger than this error term here. And this is indeed true. Why is this true? This is true because we are in case 1, and this is where the case 1 comes in. If you recall, we had this plot, this schematic plot. This was eta, and we had these two solutions. We had m, and we had m tilde, and then each of them has some neighborhood around which within which the g has to be. So I know that the g, let's say we are somewhere here. So this is case 1. I know that the g has to be either here or here. And now I show that the g, in fact, thanks to this bound, the g has to be within a distance of that point that is much smaller than the separation of these 2 points. That means the g has to be in such a ball, and therefore it cannot be here. It has to be in a ball whose radius is bigger than this tolerance radius, right? It's in fact, it's twice this tolerance radius. But because I know it's here or here, I can shrink it again and get rid of the factor 2. That's somehow the heart of this bootstrapping argument. So from that, so this inequality is not always true. So the separation between these 2 points is not always much bigger than this quantity. It is bigger precisely by definition of case 1. So by case 1, because we have, I've erased it now, but I hope you remember it. I use the fact that delta k is less than or equal to n to the minus 2 epsilon times kappa plus eta k. And that's precisely from the definition of case 1. If you recall, in case 1, I didn't state it now. Last time we discussed it as a monotonicity argument that shows that this inequality in the definition of case 1 is true not just at the threshold, but for all k strictly less than the threshold. And the converse inequality is correct for all k bigger or equal to the threshold. Okay. So therefore, on omega k minus 1, if I work on this event, omega k minus 1, I know that in other words, this distance, the minimum, so I'm close to the right one. I cannot be close to m tilde, and we conclude that, so if we are on omega k minus 1, We also have to be on xi k minus 1. This is where we had this estimate. So if we are on omega k minus 1 and on xi k minus 1, then we know that with very high probability we will be on omega k. Let me give this guy the name star. Okay? Just saying we are on omega k. In other words, this omega k just says that this bound holds without this second part here. Or the minimum is attained by this term, the first term, not the second one. Okay. So that was the sort of the main bootstrapping. This was one of the core arguments in this bootstrapping thing. So let's now. So we have controlled omega k. Let us try to control xi k. So, in other words, more conceptually, we have controlled omega k means we have controlled g, little g, or theta. We have proved such an estimate. Now we also have to control gij, the individual entries of g, and that was captured by the event xi k. So we can use lemma. Let me make sure I get this right. So these were these basic estimates on yes. So if you it was this lemma 23 which gives us estimates on the entries of G, so both on the off-diagonal and the diagonal entries of G. So if we are on the event xi k minus 1, on which we know that phi of zk is equal to 1, and on this event that we just proved holds with high probability, the notation theta. So why is that? So I clearly have the same indicator on the right-hand side, and if you recall, the estimate was that on the event phi, we had first of all lambda star plus GII minus G. This was bounded by that. So this was what we take from lemma 23. And lambda star, recall, was the guys that estimate the off-diagonal entries. So the off-diagonal entries here are estimated by lambda star, and that's just my psi theta. Okay. And the diagonal entries that I also have to estimate here, they are estimated by this one. So I will write GII minus G. This is equal to GII minus M. Right? This is just a triangle inequality. This is what I want to estimate. This one was estimated by lemma 23, and then I get the theta again here. So that was the origin of these different terms. All right. And all of this now, all that I care about is that this is in fact order n to the epsilon So let me put this, what's that? So this was of order n to the epsilon times square root of delta k. This is just, this is again something you can just check immediately from the definition of omega k and delta k. So there's some juggling with exponents, which is which I will leave to you. And yes. Okay, is this clear so far? Is that all right? Okay. So this is what we wanted, right? Because if you recall, this is, of course, this is what I was aiming at, because this is precisely the definition of CK. So if you recall, if we go back to CK, we had this guy, and we had a bit more room. We always need some room. We have these big O's, so this is a large constant, and in the definition of CK, we had an n to the 2 epsilon. So the conclusion is that on the event, so if I'm on the event, let's say C, k minus 1, and the event omega k, then the event ck holds with very high probability. And I can, if I wish, I can put in the omega k minus 1 if I wish. It doesn't really matter. I make probability smaller. So then the event ck holds with very high probability. And let me call this guy double star. Okay, and now we are basically done. So how does one conclude? You see, hopefully you see now that we can finish the induction immediately. If I have, yes, we take these two things. So this tells you that on the event omega k minus 1 intersected with ck minus 1, omega k holds with very high probability. This one says that on the event omega k minus 1, ck minus 1, ck holds with very high probability. I have this guy in addition, but I already know from the previous one that this holds with very high probability anyway, so I'm not making an additional assumption if I include this here. And therefore I have proven that if omega k minus 1 and ck minus 1 hold, then omega k and ck hold with very high probability. That's the intuition, and if you want to write this in a careful way, it goes as follows. It's maybe nice to give a name. Let's give a name to the intersection of these two events let me call this event bk, which is the intersection of these events. So I have ck and omega k. So these two estimates that I have on my board, so star and double star, they give, so if you recall, first of all, so this is not from star and double star. This was from the very beginning. This was the induction, the start of the induction, when k is equal to 0. And so this one says, it's just repeating what's on the board over there. You can do this is some gymnastics with Boolean algebra, that on the event bk minus 1, the event bk holds with very high probability. Okay, so this is a slightly shorter way of writing it. So for all, and this is for all k, remember we are in case 1. That was very important in this step that was on this board previously. We crucially used the fact that we are in case 1. So k has to be strictly less than capital K, and therefore, so if k is less than little k, we can perform an induction as follows. So we would like to estimate this by telescoping, and how do you do that? Well, you write this probability terms of two different probabilities. In terms of probability of BK, you put in an identity, or well, you write this event, you intersect with the probability of BK minus 1 and the probability of BK minus 1 complement. Okay, and this one, I can just forget about this to obtain an upper bound. So I get the probability of B k minus 1c. And this guy we just proved is small. And you can repeat this and you get so you repeat this. It's a telescoping argument for these probabilities and all of this. So every single one of these terms is of order n to the minus d. And now, of course, there's a big union bound. How big can little k be? Well, in the worst case, little k goes all the way up to the largest possible index, which is of order n to the 3. So we get an n to the 3 minus 3. So there are at least n to the 3 terms. N to the 3 because we make steps of size n to the minus 3, and we go from 1 to almost 0. Okay, but this doesn't matter. D was arbitrarily large, so we can just choose D to be big enough, and everything will be fine. Okay, so that's the proof of case 1. Okay, so we have established, using this bootstrapping, that both of these events, Ck and omega k, hold with very high probability for all k that satisfy case 1. So let's do case 2. Case 2 is in fact easier. As you recall from this discussion we did last time, case 2 is easier because you don't have to answer this, in general, somewhat delicate question of which of these two m's are you close to. Are you close to m tilde or are you close to m? And you have to make sure you actually are close to m. In case 2, you don't care because m and m tilde are so close anyway to each other that it doesn't matter. Okay. So this means, formulated in this language, it means we do not have to use, there's no need to use the hypotheses omega k minus 1. Simply because the hypothesis omega k minus 1 was used precisely to determine that you were close to, by Lipschitz continuity in the previous step, that you were close to m and not m tilde. Okay, so let's first make the observation, the following observation. That if I have this bound, that I will prove, in fact, just as I proved it before. So if I know that the minimum of these two distances is bounded by this error, which is the same as before, then theta at zk, which is nothing but the first one of these two things. That's theta. This is less than or equal to. Well, first of all, I can simplify this. This is certainly, x plus y plus x is bounded by square root of x, right? That's certainly true. If you just forget about the y, if you set y to be 0, then you certainly obtain an upper bound. So I can say that this right-hand side is bounded by square root of delta k times n to the epsilon, and then, of course, this is true if it's this the first term that is minimizing this minimum. If it happens to be the second term, then in addition I need an estimate of the distance between m and m tilde. So this is certainly always true. In case 1, this guy was much bigger than that, so this was not a good estimate. In case 2, this guy is of the same order as that one, so this is going to be fine. So this is now, by the definition of this threshold index k, going to be bounded essentially by the same thing, so by n to the epsilon times square root of delta. And I'm using this lemma 24, which we used already before, that says lemma 24 says that this quantity is of order square root of kappa plus eta k, and then by definition of k, of capital K, it was defined again precisely in such a fashion that this thing is bounded by n to the epsilon times square root of delta k. So this is order n to the epsilon times square root of delta k. Okay, so this was again now the precise version of the philosophy. This important observation we saw last time, that in case 2 you might always worry whether you're close to this one or that one. In case 2, you don't care, because the distance between m and m tilde is anyway smaller than or equal to the error that you have on the right-hand side. So it doesn't matter. Okay, so with this we can conclude the argument. So from this sharp so we therefore get the probability. So if we are on this event xk, if you recall, this estimate sharp gave us an estimate on this quantity. On the event xk minus 1, it was an estimate precisely of that quantity. And we know that on the event xk minus 1, sharp tells us that this guy is bounded by that with very high probability. But now we have just seen that this implies that theta is bounded by an order n to the epsilon times square root of delta k. And again, I have this order of n to the epsilon, so I have a constant, and I get this constant simply. I get rid of the constant simply because there's an n to the 2 epsilon in the definition of the xc. So the same observation as before. Okay. And now we can finish. Now we can do an induction. So using that now capital K We proved in case 1 the induction terminated at the largest possible index, little k, that was within the realm of case 1, which was capital K minus 1. So I know that Ck at that large K minus 1 is true, or holds with very high probability. And I use that now as the starting point of my induction for case 2. And then you do exactly the same kind of induction. I will not repeat the details. Now the induction starts when little k is equal to capital K. It's exactly the same thing as we had before. Replace the b's with x's, and you do the same telescoping argument. And we get the probability so for all k greater than or equal to capital K. And now we are done. This is the end of the proof. So why? We have, if you recall, what was Ck? So if you recall, Ck was that lambda square root of delta K. So let me write it like this. Delta K was square root of n eta K. And we have proved that this event holds with very high probability for all k, all the way down to the smallest spectral scales. And that was precisely proposition 20. We have an epsilon here, which was arbitrary, and that's precisely the definition of the stochastic domination. So since proposition 20 follows, and that's the end of the proof of this proposition 20. So that was the bootstrapping, which was sort of the heart of the whole proof, where everything comes together. And this is, I mean, you might think it's a bit complicated. Actually, it's not complicated. You just have to take some care in writing up all of these definitions precisely. This is the prototype of the proof of any local law in random matrix theory. There are about 100 papers, at least, from the last 10 years, which do exactly this argument in more or less in different ways and in more or less complicated settings. But this is, in my view, the simplest instance of such an argument. Okay, so let's stop here. Let's continue in 15 minutes, so at 18 past, and we will continue with something different. Okay, so let's continue with the next section. So what I would like to do now is to show you how to get optimal error bounds in this local law. So that is, in fact, it is a result that is useful. So getting optimal error bounds is sometimes not useful, sometimes it is useful. In this case, it really is useful. We will see in the applications starting in a few weeks. For example, if you get optimal error bounds, that is crucial if you want to understand the distribution of eigenvalues near the edges. You may have heard of the Tracy-Widom distribution, which is a famous universal distribution. It's a bit like the Gaussian. It tends to pop up everywhere, but in somewhat different, sort of more correlated type systems and so on. And it originally appeared in random matrix theory, and that's still the place where it somehow appears the most in the most canonical fashion. And in order to understand it, it's crucial to get optimal bounds for the eigenvalues, especially near the edge. So in order to do that, I would like to explain how this goes. And this is also a good excuse. So in principle, the proof that I'm about to give, one could do it using variants of the techniques that we have been using up to now. I would like to take a slightly different path, which is an excuse to present another method for doing these kinds of arguments, which is in many ways more versatile. It's, in my view, very beautiful. And I think it's generally a very powerful method in many areas of probability. And I would like to apply it to these random matrices. So optimal bounds and the proof the proof of theorem 11. So if you recall, theorem 11 was the local law where the error bound was not this n eta to the minus 1/4, but it was either 1 over n eta to minus 1, which is a much stronger bound. This was for theta, so this was for g, and for gij it was this psi, which was the imaginary part of m. So both of these are much smaller than that, and in fact both of these are optimal. We had a discussion at the very beginning of the course where I tried to convince you, or at least show some hints as to their optimality. So the goal is improve the bound So what is the philosophy? If you look at the proof that we just did, we were clearly quite wasteful in a variety of places. At some point we did this. If you recall, we had a delta k over square root of kappa plus eta k plus delta k. So we had that, and we just estimated this by square root of delta k. Right. So this is one of the things we did. So this is. If these guys are very small, if kappa is very small and eta k is very small, then this is the best you can do. So in some situations, you can't do better than that. In other situations, especially if kappa plus eta is not small, then this is clearly a very bad bound. So that's one place where we weren't very careful. But there is a more fundamental place where we are not careful, and that was the estimate this estimate that theta is bounded by lambda. Okay, so let me recall, what does this mean? Theta, what is theta? This is g minus m. And this you can write as okay. And lambda, and let me in fact, and what we said is that this is bounded by the maximum okay. And this is so this bound here, so estimating, we have an average of lots of terms, and we estimate the average by the maximum of the individual terms. Of course, this is true, but this is in general an awful bound. Imagine, for example, if these random variables, if they were, let's say, IID, imagine they were standard Gaussian IID random variables. This thing, by the central limit theorem, would be of order 1 over square root of n. Whereas this thing would be of order 1, or maybe of order square root of log n or something, depending on the tails. But there would be a discrepancy of roughly of order 1 over square root of n between these two quantities. Is this clear to everyone? So this is a big waste. Now, one of the difficulties, and that is in fact a major difficulty in this business, is that when you calculate, you want to estimate such an average, these random variables are not independent. If they were, you see, if I take an average, how big is this thing? So let's say xi is a random variable, xi has mean 0. Let me take some random variables xi, which have mean 0 and variance 1. So if these random variables, so the first case, if they are independent, let me call this quantity A. So if xi, if they are independent, A is of order n to the minus 1/2. Okay, that's the central limit theorem, for example, in probability. The opposite extreme if they are all dependent, if they are all the same, then A is just equal to x1 and A is 1. So if they are fully dependent, then this thing is of order 1. So how much you gain from this averaging depends on how independent these things are, and these are the two extreme scenarios. So you will gain anything between nothing and 1 over square root of n. It turns out in random matrices, for random matrices, these random variables, they are somewhere in between. They are neither fully independent nor fully dependent, and in fact, what you gain will turn out to be 1 over square root of n eta. That's going to be the gain. So this shows with this philosophy that if eta is of order 1, so if you're on global scales, then these guys behave like independent random variables. And if eta is of order 1 over n, so you are on the microscopic scales, then they behave as if they were fully dependent. That's roughly the philosophy, and this mechanism is something we would like to understand. And this mechanism is necessary to obtain these kinds of sharp bounds here. So to do this in practice, so historically there are at least 10 papers that address this problem. There were different approaches. The initial approaches were unbelievably technical and unreadable. Extremely difficult, and these proofs have been streamlined since. The difficulty, you probably see why this is not such an easy task, is these things you have to estimate such averages of dependent random variables, so you have to somehow control the dependencies, and this can be quite complicated. And there are all sorts of hierarchical expansions, sort of unwrapping these dependencies, which do the job. And currently these kinds of arguments have been cleaned up to a reasonable degree. I would, however, like to present a different approach, which is in many ways much more elementary. It's very powerful, and it almost circumvents these kinds of issues of unwrapping the dependencies. It's sort of baked into how the process works. I think it's a very nice argument, and as I said, it's a very general argument. It's a fact about an argument that can be used in many contexts in probability theory. So how does it go? So we use a new approach. I mean, a new in the sense of new as opposed to what we did before. I mean, this approach is, of course, present in the literature. So this approach has a variety of names. Some people call it the Cumulant Expansion. Or it's also known as the generalized Stein method. Does anyone know the Stein method? Has any of you seen the Stein method? No, for proving the central limit theorem. It's one of the three classical proofs of the central limit theorem. There are three classical proofs. You've probably seen the one using characteristic functions. There's this one by Stein. So we will not actually do it because we don't need it, but the ideas are based on generalizations of his method. So how does it work? Well, as its name implies, it relies on cumulants. Does anyone know what a cumulant is? Has anyone seen a cumulant? No cumulants. Okay, kind of. Well, let me define what a cumulant is. A cumulant is a very important object in probability theory and statistical physics. So let me take a random variable h, a real valued random variable with finite moments of all order. So all of its moments exist and are finite. So we will define the kth cumulant. Moments, you know, right? I mean, we've talked about moments, so you must know the moment the kth moment of h is by definition the expectation of h to the k, right? So cumulants are versions of these moments which have been appropriately centered, if you wish. So k, the kth cumulant of h. So the kth cumulant of h is. So there's the notation I will use. So it's ck of h. So let me write a formula which is not the formula for the cumulant, it's the formula for the moment. How do you get, so the moment is of course the expectation of h to the k. There is another way of writing these things, which is a very good way, which is to take the so-called generating function, or the characteristic function, and then you differentiate in t, right? So I put in these i's. These i's are a nuisance. If you assume that the random variable has sub-exponential tails, then you can ignore the I. However, if you only assume it has finite moments of all order, without the I, this would in general not exist. So I need to put in the I. It just complicates the algebra a bit. But if you wish, you can, every time you see an I in what I write, you can just drop it. And the formulas are algebraically correct, provided you make slightly stronger assumptions on your tails. So how do you get this kth moment? Well, you differentiate in t k times, and then to compensate in these factors of I, you have to have a minus I to the k. Okay, this is clear, right? So if I differentiate this guy k times in t, I multiply with minus I to the k, and I set t to be 0, I get precisely that. Okay, so that's the moment, and the cumulant is, so this is called the generating function of the moments, and the generating function of the cumulants is just the logarithm of the generating function of the moments. So that's how cumulants are defined. I think this is the best definition. In the exercises, there will be another combinatorial definition. As it turns out, there's a nice and simple relationship between moments and cumulants, a combinatorial relationship. So a few preliminary observations. The moment of order k is homogeneous in h of degree k, right? So which means if you multiply h with a parameter lambda, a positive deterministic number lambda, then you will multiply the kth moment with lambda to the k. The same thing is true for cumulants. Just by the chain rule. Right, just by the chain rule of differentiation. So these are also homogeneous of degree k. And in particular, if you recall my random variables hij, by assumption, so let me assume they are real valued to simplify things, let's assume we are working with real valued entries. If you recall, these Hij's were designed in such a way that if I multiply them with square root of n, I get a random variable that has uniformly bounded moments of all order. That means if I put in the square root of n times 1 over square root of n, this variable has finite moments of all order. I can do the differentiation and I pull out this 1 over square root of n and I get n to the minus k over 2. So this is of order k n to the minus k over 2. Uniformly in n, I, and j. Okay, the constants depend on k, but they do not depend on I, j, or n. Okay, so this is what a cumulant is. As I said, it's a fundamental object in much of probability, also statistical mechanics and statistical physics. There's a high chance you will encounter it in some other class, perhaps in the course of Bellenic, Ivan Bellenic. The reason why these things are so useful for us is the following beautiful formula. So to me, it's a beautiful identity, and it's also extremely powerful. You will see how. I mean, you can do many things with it. You can use it to prove the central limit theorem, for example, in a very easy way. We will use it for different purposes. So the formula is the following. Let me take a C. Well, in general, I just need a ck function, but let me just take a C infinity function on the reals, and it can be complex valued. And and h is a real valued random variable, like above. With finite moments of all order. With finite moments of all order. Then you have the following expansion. And the expansion it computes the following thing. So you take your function f of h, you multiply it by h, and you take the expectation. This thing can be expanded as the following series. So you have the following series, which is called the Cumulant Expansion. So in other words, the expectation of h times f of h is given by such a series. So the coefficients are precisely the cumulants of h, and then you take the expectation of the kth derivative of f at h. And then you have a remainder term r, which ultimately, as you might imagine, comes from some Taylor expansion. And we are not really interested in the specific form of this remainder term. It's always going to be small. We just have to estimate it as in Taylor's theorem. And a good bound that is going to be sufficient for all of our purposes is the following. Okay, so this error bound is not particularly interesting. You will see in the applications it's relatively easy to show that this thing is small. You will see, for example, we will use it. So we will use it for our matrix entries. This is typically the kinds of objects on which you use them. You use it for random variables whose cumulants decay rapidly. Right? These guys decay rapidly. So if you choose your k to be sufficiently large here, or your n to be sufficiently large, then this, okay, so then this h here, this moment of the h is going to give me factors of capital N to the minus little n plus 2 over 2, which is going to be tiny. And then I have these L infinity norms to worry about, and this can be, and this form is basically sufficient for all applications we will need. So you should really think of the cumulant expansion as being this guy, and the remainder term we will deal with, but it's never really a problem. So why is this such a beautiful identity? So you will see how it works in practice. It works extremely well. One great thing about it is if you stare at this identity a bit, you can see the central limit theorem basically immediately. Yes, you have a.
In the remainder, there are no n plus 1 factorial denominator?
No, but there could be. So these bounds, they depend on n. That's maybe a good observation. So this is for all fixed n. So these bounds, they depend on n. But we don't really take, you never take the limit n tends to infinity. You always fix your n, and we don't really track the n dependence of the bounds. So how do you see the central limit theorem? Maybe we can have a little exercise, but I will explain to you the idea. Look at these cumulants. So first, what is the zeroth cumulant? That's just 0. Okay, I think that's correct. So if you don't differentiate at all, you have just a log of 1, which is 0. Okay, so C0 of h is equal to 0. C1 of h, if you differentiate this once, you will get you get the derivative of the log. So downstairs you get 1, right? Because you set t to be equal to 0. And upstairs you get the derivative of this guy, which gives you the expectation of h. So this gives you precisely the expectation of h. C2 of h, you can compute this. It's a 2-line calculation. I will not do it. You can do it for yourself. It's a very easy calculation. You will find the variance of h. So the second cumulant is nothing but the variance of h. So here you see this is the philosophy that these cumulants, they're a bit like moments, but they are sort of appropriately centered, where you subtract moments of lower order in a suitable fashion. And the variance is just the second moment where you have subtracted the first moment. Now, so these are the two first basic moments. Does there exist a random variable whose cumulants beyond this are all 0? Cumulants of order 3 and above are all 0. Can anyone think of such a random variable? You can just stare at this formula. What does it mean for this function, for the derivative of order 3 and higher of this function to vanish?
Gaussian.
It's a Gaussian, right? Because it means that this must be a polynomial of degree at most 2. Okay, the logarithm. And therefore, this thing must be the exponential of a polynomial of degree at most 2. And that's just the Gaussian. It only leaves the Gaussian. So the Gaussian is uniquely characterized as the distribution on the real line whose cumulants vanish beyond order 2. Now what you can do is you can take H You can take H to be the following random variable. You can plug things in here. You can apply this cumulant expansion. You can take n is equal to 2, I think is already enough. And you will be able to show that, that all of the higher order cumulants vanish in the limit capital N tends to infinity. If you take x1 up to xn being independent centered random variables. So you just plug things in. I will not do this for you. You can do it yourself if you wish, because we won't need it for this course. But just by the scaling, you see, you will. I mean, it's not hard to see. You can do it yourself if you wish. That the terms k is equal to 0 and k is equal to 1. They give you a contribution, but k is equal to 2 and higher. They will vanish in the limit capital N tends to infinity. And this will show you that this h in the limit as n tends to infinity will satisfy such a cumulant expansion with just 2 terms here. And this is true for all f's. And if you can choose it for all f's, this uniquely characterizes the limiting distribution of h as the Gaussian. So this is basically in 1 minute the idea behind Stein's proof of the central limit theorem. So it's conceptually a very appealing argument, and what we are doing here is we are doing a sort of quantitative, more precise version of this argument. We will have to expand much further. We are asking harder questions, and we are also doing more precise estimates. But the basic philosophy is really that one. Is this okay? So let me prove this. The cumulant expansion. It's now I've given you the definitions, so in principle it's just some algebra and using Taylor's theorem. I'm sure if I gave you an hour you would come up with the proof yourself, but one has to, the proof is very easy if you do it, if you start correctly, and if you start wrong it becomes a big mess. So let me start. We will prove it in the usual way of first proving it for a polynomial and then using Taylor's theorem to extend it to a general function. So let me call chi of t this generating function. The generating function of my cumulants. So let's take an m now, and the real idea behind the proof is to write this object, which we know, this is going to give just the nth moment, right? If you take I took the log and then I take again the expectation and I differentiate this m times, I will just get the nth moment. So this is a complicated way of writing something simple, and I will do this in 2 steps. I first differentiate once and then I differentiate m minus 1 times. And now if I differentiate this guy once, I get chi prime of t e to the chi of t. Right? This is just differentiating the exponential. And now I apply the Leibniz rule for differentiation. So if you take the m minus first derivative of a product of two functions, you know there's a binomial theorem for derivatives, which goes as follows. So I call k the number of derivatives acting on the first guy. So you would usually write this as a k going from 0 to m minus 1, but instead I just relabel my summation index as going from 1 to m. So this guy gets k minus 1 derivatives, so chi itself gets k derivatives, and then I have I get that. And now I can specialize. So if I take the special case of I just set I take the expectation of all of this, and I set t equal to 0 at the end. So I can write the mth moment of h as we discussed. This is just by sort of by definition, right? So this thing was the logarithm of the expectation. If I take the exponential of that, then I just have this guy, and that clearly gives me the mth moment. And now I can plug in my formula. I take this formula and I set t to be equal to 0. This guy, when t is equal to 0, is just by definition the kth cumulant. Right? I have these factors of I, but I chose them in such a way that everything works out nicely. And this guy, when t is equal to 0, is the m minus kth moment. Okay. So now, this is what I got for this was, if you wish, this is just a complicated way of writing the mth moment. So you may think, what is this good for? The point is I can write this in the general form. So if I now choose my f of h, which is equal to h to the n, we get the following fact. So this is just going to be h to the n plus 1. So I set m is equal to n plus 1. And I will get this formula. So k goes from 1 to n plus 1. I have an n, choose k minus 1. And then I have ck of h, and the expectation of h to the n plus 1 minus k. Okay, so I'm just stupidly copying this formula. But now, maybe I can do one intermediate step. I will rewrite this Okay, I can shift my summation index. Okay, going from 1 to n plus 1. Oops, it goes from 0 to n. And I would like to express this not in terms of some power of h, but in terms of the original function f. And you notice that this is the kth derivative of h up to some combinatorial factors, which are precisely the combinatorial factors in the numerator of this binomial coefficient. Okay, so this is just n times n minus 1 times all the way down to n minus k plus 1, which is exactly what you get if you differentiate h to the n, if you differentiate h to the n k times. So by linearity, so both sides, I have established this identity for the function f being equal to h to the n, some power. And notice that both sides are linear functions of f, and therefore I can take arbitrary linear combinations of powers, and the equation, this will remain equal to that, and therefore this applies also for any polynomial. Provided, so here it was important that I expanded. Here I expanded up to the degree of h. So here this n has to be was the same as the degree, and of course this also works if this n is greater than the degree. Then I just start getting zeros here, right? If I differentiate the polynomial more times than its degree, then the terms in the sum vanish. So by linearity, the same formula holds for h being a polynomial, for h a polynomial of degree h, yes, f, thank you. A polynomial of degree less than or equal to n. So if you take a polynomial of degree less than or equal to n, then the result of this cumulant expansion is exact without a remainder term. So now we have proved this cumulant expansion for all polynomials, and then the general case follows by Taylor's theorem. So I will not do it because it's not particularly interesting to do it. I mean, I think it's extremely plausible that this can be done. If you want to, you can try to work it out. So I will leave this as an exercise. And I will put a little star in the sense that it's. I mean, if once you know how to do it, it's not extremely long. It's maybe a page or so. But I think you will not. I mean, if you just sit down for 5 minutes, I think you will not get it. I mean, it requires some thought, especially to get this form of the error term. But I think it's not particularly fascinating for you to watch me do it, so I will not do it here. You can also find it in the literature, so I can give references. I think maybe we can have a star exercise, and then we can have references as well, where this approximation is done. But this is the key idea. I mean, you prove it for a polynomial. Once you have it for a polynomial, then by Taylor's theorem, it's kind of clear it's going to extend somehow to smooth functions, and this is how it goes. Okay, so this is the cumulant expansion that we will use in order to derive these bounds. We'll see next time how it goes. you will see it is there are basically there are two known approaches to prove these local laws in random matrix theory. As far as I know, there are no others, and this is a nice opportunity to show both. So the first one, which is historically also the first, is what we did up to now to prove this weak local law, and this is another way, which they have advantages and disadvantages. This is generally more versatile, and generally I think it's more powerful, but it has some disadvantages that do not make the other one obsolete. We will see next time how this works, and I think, yes, so we'll stop for here today and continue next time with the applications of this cumulant expansion.